Hello. Hello. Wow, this mic is loud. Everybody say hi to Blackberry. She's here for the algorithm. She's doing what she does best. Being cute. Hi everybody. So today we have an A1706 that came in the shop. It is not turning on. So let's get into it. Hope everybody from the US had a good holiday weekend. So here we have an A1706. It's already been opened. So not turning on from the customer. So let's start our function check. First thing we're going to do is take a amp meter. Plugged into at least an 85 or 87 watt USB-C charger. You always have to use at least an 87 watt. If you're troubleshooting 16-inch MacBooks, you have to have the 96 watt. Plug it in, and what does it show us? It shows us 5 volts, no amperage. Okay, we'll try another one. We'll go around the board. We don't have to try both sides in our initial check. We'll go around the board and see if anything is giving us anything different. Ooh, that's a stretch. $5 volts and 0.02 amps, so doesn't look like anything's working. Okay, so all 4 ports are doing pretty much the same thing. We get 5 volts and no amperage taken. 0.02 amps is pretty much no amperage taken. Oh, can't see that. So we need to go look at something that's affecting all 4 sides at the same time. When you troubleshoot these, you plug it in. Most of the time you get one port that will not work the same as all the others. So we have the whole board is being affected here because all ports are doing the same thing. So we can't just blame like one charging chip for this. We have to go for something more central. So the first thing I'm going to check is the main power rail. Anybody tell me what the main power rail in a MacBook is? I think my latency is high. PP bus, there you go. David, first one. So first thing I'm going to check is PP bus. So I know where it is right away, but let's go to the schematic and board view. Schematic. That didn't work. There we go. So schematic and board view. I'm going to hit Control F, and we're going to search for PP bus. So PP bus G3 hot, that's the one we're looking for. Search, and it shows me everywhere where PP bus is. So let's see, this giant thing right here, F7000. So that's a good spot to find it. So that's F7000. It's a fuse. It's a nice big piece. It's up in a corner right here. Pretty easy to find. Go back to our overhead. So that is right there. This big white thing right here. Zoom in on that. That white square right there. Focus. There you go. So let's see what PP bus is. Black on ground, red on the end of that fuse. I have millivolts. 54 millivolts. I'll try the other side of the fuse just in case the fuse is burnt out. Same thing. So we have no PP bus. So PP bus is the main power rail for the board, but it's not the most important power rail for getting your charging voltage started. the most important power rail for getting your charging voltage started is 3v3 G3 hot. So these are the charging chips here. These guys are the 4 of them, one for each charge port. They run on PP3v3. So let's check out where PP3v3 is. So let's do another search. PP3v3 G3, that's not here. PP3v3 underscore G. There we go. I double clicked. Yeah, okay. So right where we were working at, the big fuse is right here. So right underneath it, we have this inductor, and there's PP3v3 G3 hot. That's reg R. So that's just the before, like right out of the regulator, and there's PP3v3 G3 hot. So we'll just stay right underneath the fuse. It's this next component right here. So we'll look right at there. Making noise, I see. One moment. Still mic making noise. Why mic making noise? Sorry, headphone users. Alternate mic. This is going to sound absolutely terrible, but let's do a mic repair stream for a second. Okay, so obviously this it's either this connector or this wire has broken. So let's see if the connector itself is broken. Ohm check from here. I think that's this guy down here. That's working. Tip, ring is here. That ring? Ring should be working. Yep. And sleeve. No sleeve? This is sleeve. Okay. Connector's working. Let's take a look at this wiring a little bit. Something might be touching here that's not supposed to be touching. Oop. Snip. Oh wow, these cutters are terrible. Strip the cable. You got to separate the. So this is a shielded audio cable, so the ground is all around the signal cable, which is down the center. So then we'll twist the ground off to the side, and then we'll have to get rid of the fiberglass reinforcement. Reinforcement gone. Now I need to clean up this connector a bit. Soldering on. Can I have some fume extraction? Okay, yeah, that fume extraction is really freaking loud on this camera. This is going to get really hot in my fingers really fast. I need pliers. So I can use these. The very end is not sharp in there, so. Gotta get the holes cleared. There's the solder vise thingy all the way on my desk. This is a impromptu repair, so that thing is going to be hot. I don't want to touch it. I don't want to touch it. I touched it. Ah, that's hot. That's hot. Okay. What else needs to be cleaned out? You bring me pliers instead of omni-vise.
I can hear Omnivice. Starts getting pliers because pliers.
Okay, that's good enough. There's still some copper left from before, but who cares? Okay, strip this off a little bit. I think that guy's good as I hoped. Somewhat stripped, but I bet we put a little bit of solder on that and it'll clean itself right up for us.
Device of much gravity?
Ah, the device of gravity. The device of gravity is here. There we go. Held by device of gravity. And let's tin these wires up. Attach them. Always make sure whatever furl needs to go on before you attach it, make sure it's on. Key point. Even the best of us forgets to put that crap on there. You might have a little bit too much solder to get through the hole. Yes, it is. Okay. Let's clean out that solder. Go one through both points. Solder that one on first. That'll hold it. And get the back one on. Find some to burn. That looks good. Now the ground, which I will over solder and then nip off. Let me just add some solder to that. There we go. Add a little bit of flux. Solder the ground right in there. Even though this has a strain relief, I would still like to solder the ground shorter than the signal cable, because the ground is a lot more substantial than the signal cable, so it acts as a strain relief a little bit. Trim off our excess. Okay, let's see if this works now. Hot. Rapid cooling. Connector rapid cooling. Okay. This might sound crazy when I plug this in and if it turns on. Test one. Test one. Hey, look at that, it works. So let me put this all back on here. You can turn off the fume extractor. I got my Stream Assistant Hi-Hi here. Let's case it back up. Oh, the plastic goes on first. Strain relief. This gets pinched in there. I'll put this on. I'll put that on. And slide the ferrule nut up. Let me push in the wire a little bit. In. It's already preloaded with strain relief. And there we go. Test one. Hey, look at that. And now that should sound a lot better. And no more popping. All right. Okay, back to the task at hand. So here we have an A1706 MacBook Pro with no charging, or no turning on, no anything. We just function checked. All 4 charge ports are giving us 5 volts with no amperage usage. So 0.03 amps and 30 milliamps, that's not any amperage usage. We checked for PP bus G3 hot. We don't have PP bus G3 hot, and we were just looking for PP3v3. So if I go back to the schematic and board view, we can see where PP3v3 is. So we check for PP bus on this big fuse, and now we want to check for PP3v3 on this little resistor right here. So zoom in. So this is the fuse we checked on here. A little resistor right underneath there. Man, that has a shallow focus. Little resistor right underneath that there. Kind of hard to see from here. Bring it under microscope. So that's the fuse we checked at. And now we're going to be checking for PP3v3 on that resistor right in the middle. So my black probe on ground. Oops. Microscope, multimeter. There we go. Looking for voltage. And we're going to check PP3v3 for voltage. We have 1 millivolt on PP3v3. So we don't have PP3v3. So PP3v3 is what powers the CD3215s for them to communicate with the charger to make sure we get 20 volts. So we have nothing on PP3v3. 0.8 millivolts and it's going down. My multimeter's draining out whatever electricity was in here. So now this is the system side of PP3v3. This is the creation side of PP3v3. This is the circuit that creates it. So we check there. Yeah, that resistor is not blown out. It's not on either side. So this is the coil that creates it. The coil probably is not going to be burnt out. So we need 3 things for a good power rail. For any power rail, doesn't matter what power rail it is on the machine, we need 3 things to create that power rail. We need a good path for the power to go. So the power rail can't be shorted. It has to have a safe path for it to go. We need a good source to create the power from. And we need the enable signal for that chip to create the power. So there's 3 things that we always need for every power rail on the entire machine. So first thing we're going to check is to make sure that PP3v3 is not shorted. So I'm going to remove power from my board. I'm going to switch to ohms mode, and we're going to check to see if PP3v3 is shorted. Because if there's a short on PP3v3, we can't create the power rail. We have 10 kilo ohms to ground, so nope, that's fine. So the next thing is, do we have enable, and do we have a good source for the power? So I'm going to plug power back into this. So if we go back to the schematic and board view, here's our system side of PP3v3. Here's the creation side. This is the circuit that's creating it. So if we go over here, this is the actual chip that is creating PP3v3. So let's bring it up on the schematic. So here's the actual chip that creates PP3v3. Here's the inductor for it, and then it goes out to system from here. So we need a good enable is the next one. So here's the enable, EN. So power management enable 3v3 G3 hot. So PM EN 3v3 G3 hot. So on pin 10, so we come back over to here and look at pin 10. So that's what we want to check. It's a little tiny point here. There's a bigger point up over here. So we have, this is our chip. That's the little tiny point, and you can watch, you can follow the trace up to that other point over here. So either one of them we could check. So I'll go for the bigger one, easier to put onto. And we have 2.2 volts. So that's a good enable signal. 2 volts should be a good enable. So this should be enabling right now. So now, what's the last thing? Anybody know what was the last thing that I said? So we need a safe path for power. We need an enable for the chip to make the power. What's the last one that we need? The source. Exactly. We need a good source of power. So if we go back to the schematic and board view, let's find out where our source is. So if we zoom out a little bit, what does it say here? BSTLX, no. Out, no, that's where it's going out. Bias, no, that's how it creates it. These are all grounds. Reset, enable, the mode of the chip, that's not even used. Sup, that's probably supply. So let's follow that back. So we have a diode here, PPVin G3 hot. So primary power voltage in. That seems like that's incoming. What is it coming from? Either PP bus or PPDC in. So this here is an isolation diode. You want this is an important rail that makes everything communicate with everything. So we want it to power from either the battery or we want it to power from the wall when the battery is dead. So we have this here. PP bus G3 hot will be working from the battery, but if the battery's dead, we don't have any PP bus G3 hot. So PP DC in G3 hot comes right in here. So this is the DC in right from the charger. Comes in here, but we don't want that feeding back to PP bus. So we have 20 volts coming in from the charger. We don't want that feeding back into PP bus and put 20 volts on PP bus. So we put this double diode, this double protection diode here. So either one of them is going to power this. So we have, right now we have 5 volts on our charger. So we should have 5 volts coming in here on one of these sides. We should have 5 volts. And then on the other side, we should have 5 volts coming out over to here. So let's go ahead and take a look at that. Let's find it first. So D6902, I'm going to right click on that. Oop. Right click on that, search D6902. Oops, wrong way. I meant that way. There we go. And it shows up right on the other side, thanks to Paul Daniels' awesome software. So here we have PPVin G3 hot, so that's what's going out to the chip. And here we have PPDCN and PP bus. So we should have 5 volts here, and we should have 5 volts here. So let's check that. Microscope. So that's the chip in question. So we should have 5 volts here. We have 5.17, perfect. And we should have 5 volts here, and there's a test point, so I'm going to go for the test point. 1.3 volts. Well, we can't create 3.3 volts off of 1.3 volts when it's only a buck converter. Boost converters can do that, but this is only a buck converter. So we cannot create 3.3 volts off of 1 volt in this circuit. So something is wrong between here and here. Between this chip and here. So I will remove power from it. First thing we're going to check is if this has a short on it. So we're going to switch back to ohms. Black probe on ground, and I'm going to check this for a short. And we have 220 ohms. That's a short. This should be up in the kilo ohms somewhere. So 220 ohms is short. So let's go back to the schematic and board view. So this is what we're working on here, this side. If I zoom out, we have a couple things that are on it. So what is this up over here? We have a capacitor, we have the diode, we have the chip that creates PP3V3. Another capacitor here. I'm going to click the middle mouse button, flip the board over, and we have another capacitor here. And we have the ISL here. So now is the time, since I have to look at the bottom of the board too. I have 1, 2, 3 components on top, and then on the bottom of the board I have 2 more components to look at. We have to remove the board from the case. I have not done that yet, so... Time for some screwing. Just some screwing around on stream. Okay, so I'm going to take my wow stick. First, I'm going to go around and take off all of the T3 screws, because the T3 screws are all of the caps and miscellaneous stuff. It's not actually holding the board in. So let's go around and take out all the T3 screws. First, we have the touch bar and the charge port. The other touch bar connector. Display connector. Yeah, this is when I should be able to fast forward through with just some quick techno music or something. This is live. This is real life. I have the trackpad connector. Another important thing to note is that all this testing is done with the battery disconnected from the system. Sensationalist wants the Oots mix. How about the Boots and Pants mix? Boots and Pants and Boots and Pants and Boots and Pants. Okay, that should be all the... Oh wait, there's 2 T3 board screws that have to come out. Oots pretzels, yes. So you're from in this area. Oots is a Pennsylvania brand. I don't think they're much out far of the New York, New Jersey, Pennsylvania area. Okay, now we'll switch over to our T5. And this is all of the structural screws for the board holding in the case. Underneath the sticker here is the battery screw. So even though the battery connector is connected, the battery is disconnected as soon as you remove this this little wire. This little wire controls some MOSFETs that are on the battery board. And if this is disconnected, the MOSFETs are no longer in connection with the board and everything. So this is completely dead. If you ever disconnect this and you still have power from the battery, that's a bad battery. China has been going nuts with their battery production. They've had some really bad batteries coming out of China. And if you ever get one that you don't even need to have this little cable plugged in, that you, as soon as you screw this in, the machine's turning on with this cable disconnected, get that battery out of that machine and throw it away immediately. They are dangerous. Okay, that's all of our screws. Now we go for connectors. So, touch bar, charger, microphone, touch bar, speakers, Wi-Fi and Bluetooth antennas. I already popped off the display. Trackpad, keyboard and fans, other speaker, this tape, yeah, there you go. charging port, audio port, headphone port, and power button. Be careful with the power button. So this power button has a wire attached with it, and the wire is glued to the board right here, right where there's circuits on the wire. So you have to get your tweezers underneath the wire and separate that first, and then you can pop the connector off. Okay, now we could lift the board from the machine. I always rock it back and forth because it helps move some of the connectors out of the way, and it'll help show you where it might be hung up, where you might have forgotten a connector or forgotten a screw. Because if this connector was still connected, you'll see it pivoting around that one spot. If this connector was connected, it pivots at a different spot, and it'll lead you to what you may have missed. If this was still connected, it will pivot around that spot, and then you can home in on there and find something that you may have missed. Okay. Board is freed. Now, very first thing, visual inspection. So we have narrowed down the system that we have a problem with, is PP3V3. We know the couple of capacitors and couple of things that are with it, so let's give it a good visual inspection under the microscope. So we're looking for a short. Most things that short on a board is going to be capacitors or sometimes chips. So you got to look at these capacitors, the capacitors that we know are in the system. You look at them at a very steep angle. We zoom in on the one capacitor, and we look at it at a really steep angle. And if you're lucky, if it's broken, it'll have a crack down the side of it. And you'll be able to see that it's broken before actually removing and testing. Let's get it off the edge of the table so I can get a better angle. Okay, where am I? There am I. So that capacitor looks okay. There's no crack down the side of it on either side. Let me look at the schematic again on which capacitor I'm looking at up here. Okay, it's the one next to the 3 horizontal. It's the vertical next to the 3 horizontal. So that one right there. It's this one that I'm looking at. That looks like it's a cracked. Let me see if I could get that on screen. Okay, a little brighter. Try to steady it some because I'm holding it out in the middle of the air. See that white mark on the side of it? That's a crack. That's a cracked capacitor. So that's our problem. This one little capacitor that is that small, this is my pointer finger next to it. That one little capacitor brought the system down. So just for the hell of it, we'll keep looking at the other stuff too. This is the other capacitor that's in the string. That one looks okay. And this is the ISL, and it's that bottom left-hand corner is where it goes to. So I'm going to make sure there's no green stuff, nothing hanging out from it. We can actually probably see the ball that it goes to underneath the chip. The right angle, yep. Some dust on the one capacitor pointing at it, but everything looks nice and clean there. So I guess it's just that one capacitor that's cracked. So that right there, that little beige white spot there, that's a cracked capacitor. So let's just pull this one off. Let's first see if it's just going to pop right off, and then we can make sure that it clears the short. There's a lot of things around here, so I'm not going to try too hard to pop it off. No, it's going to take too much force. I'm going to wind up hurting something else, so we'll take it off with hot air. So a little bit of flux. My hot air is full and full, as it always is when I solder. Try to get all that flux on it. There we go. Okay, that's off. Now we can check and see if it's still shorted. I'm just going to go back to where we were working on it before. We were on the output of the diode there. So my black probe on ground, and we'll check here. We had like 200 ohms before. Now it's growing at 2.7K, 3K, 10,000 ohms. That seems completely normal to me. So that was it. It was just that one little capacitor right there. So now we'll grab a stack of donor boards and we'll see if any of these have that capacitor. Let's see, it's right on the top here. So yep, this first one that I grabbed, this one has the capacitor. Good. So a lot of these capacitors have the same value on the board, but there are many different values all over the board. And there's no way of telling what value any one of these capacitors have, or any one of these little guys have, without having a schematic and board view handy. The big ones, like these big guys, we can read the stuff on it, and we can find out what that all means and what value it is and what type of capacitor it is. But unless we have schematic and board view, we can't tell what this one is. It's probably not super critical to have it in there. So if you're in a pinch and you find something like this and there's a couple of capacitors on the string like that, you can probably get away with removing it. But since there's only 3 on this string and this is an input for a buck regulator, I definitely want to replace it. Because these capacitors keep the voltage smooth on their way in. So out of the microscope camera, I am heating up the donor board. And I'll take that one off, and then we'll bring it in and replace it there. Here's our new one. Float into place, stands up straight, good. .603 size, I would say 2.2 microfarad or 6 to 6.8 microfarad. Let's take a look. We know exactly what it is because we have the information. So this is the guy that we're looking at right here in this little mess. So I'm going to right click on it, search, and it brings it up on this side. And 2.2 microfarad, 402. So a little bit smaller than what you thought. We're working with a 402 capacitor. And it's 35 volt, 2.2 microfarad. So the 35 volt is important too, not just the 2.2. The 20% doesn't matter, they're all about the same. But the X5R is not exactly important, but most of them are about the same. They're all that X5R range, whatever brand that, not brand, product line that is. 402 is the size, 2.2 is the capacitance, and that's the number on the board, C7081. So that's replaced. The board is still hot, so I can't plug it in. Do those capacitors have a polarity? Some of them do. This one that we're working on does not. You can see on the schematic here, it has 2 straight lines. So these don't have a polarity when they have 2 straight lines. I'll go back to the microscope here. So these big guys here, they have a line on one side of it. This line on the bigger ones indicates the positive side of the capacitor. So if we look at this one here, if we bring this one up on the schematic and board view, so that's this big dude right here, 7051. So right click on that, search, and you see that it has it's denoted which one's positive. Oh, that's not on screen for you. It's denoted which side is positive because it has a little plus, and it has 1 straight and 1 curved line. So the curved line is the anode, the straight line's the cathode. Did I get that right? Yeah. And so this one does have an actual polarity. All the ones that have two straight lines, that's no polarity to them. And that's also what you see on the board itself. All these little ones, no polarity. The big ones that have lines on them and stuff, they have polarity. Okay, this board feels about cool enough. I do not have a charge port here. I don't see a charge port here. One moment, please. I should have switched to the BlackBerry cam while I went away. Cat cam. Aw, she's not playing anymore. She was playing when I walked over there. Oop. Okay, so I have a extra charge port here. Oh, hey, JP. I'm sure the guys would take them over there. I wouldn't mind one. Extra charge port. Now we can test it outside the machine. So I'm going to plug it in. Let's see what we take. 5 volts, no amperage. 0 amperage instead of something like before. Let's see what we have. First I'm going to check PP bus. PP bus is still down. And let's check PP3V3. PP3V3 is 2.2 volts. So yeah, that's not good yet. 2.2 volts isn't enough. Okay, so what I think is going on here, before I even test anything more, what I think is going to happen here is I'm going to find out that the output to that diode we measured before is still going to be low, because this machine was probably charging at 20 volts when that little capacitor blew up and shorted, and it hurt this diode. So this diode's not providing enough power anymore because it's semi-burnt out. So let's check the input to the diode is 5 volts, and the output of the diode is 3.9 volts. So that capacitor hurt this diode. That diode's hurting. We need to change the diode too. Back to my donor pile. Oh, good. The same donor board has a new diode. There's our diode. So the capacitor that went bad, up here, this guy, is on the output of this diode. So this diode probably had 12 volts coming through PP bus and possibly 20 volts coming through the charger if it was plugged in. The instant that capacitor went bad, it overpowered this diode. This diode had to handle way too much power, so this diode is halfway burnt out inside, so we have to get rid of that off the board. So for this one with the big pads like that, I like to add a little bit of fresh solder to it. Not completely necessary when there's no liquid damage. I just like a little bit of fresh solder. Not that big. Yeah, about like that. And we'll give it a little bit of flux for when the new one comes down. Sent you a random assortment of donuts from the donut pub. Awesome. Thanks, JP. That sounds interesting, the donut pub. You always find interesting and cool things around here that I didn't even know existed. Okay, I'm heating up the donor board off camera. Okay, I have my new diode. I'll bring it in here. Try to get it to center. There you go. That looks good. Okay, new diode installed. Let's let that cool off and we can test it again. Hi, Rob. Next time, make it a Jimmy John sampler platter. Got to be earlier for that then. Everybody here has already had lunch, and it's too close to lunch to be eating more food, unless we all just take it home. Those rectangular SMD ones have marking on the positive side, correct, instead of the negative side. Yes, SMD has the positive side. It's so utterly confusing. I don't know why they ever did that. But anything through hole, all of the through hole stuff, old stuff, has the negative side marked. All of the SMD stuff has the positive side marked. With a and it's usually a white line, like you would expect on the through hole stuff is a black line. But all the SMD is a white line, and it's on the positive side. Are you cool yet? No, I should employ the rapid cool technology. This is awfully warm, so... Get the fume extractor nozzle in here. I'll turn the fume extractor on. We've been doing very little soldering, so I haven't felt a need to turn on the fume extractor. But rapid cool. I thought the round SMT electrolytics also had the negative marked. Let's see. It's very rare that I have to change any of those. Those round electrolytics, they don't go bad often at all. Let me find a board that I would have the schematic to easily. They don't use them anymore. It's all the really old boards that have the SMD electrolytics. You don't see them anywhere anymore. Like, this is a really old board. And we have a couple electrolytics on here. But let's see. Let's open up the schematic and board view for this board. What is this one? 29 bad SMC. Oh, that sucks. 29, 30. No, what is this thing? This is really old. This is a 2010 2879. The 2010 MacBook, 2879. That's the ones that use these electrolytics. You don't see them anymore. So, that should be cool enough. Yeah, that's more than cool enough now. Rapid cool works well. Let's go on a little exploration here, a little journey of knowledge. So where the debate is on the marking of capacitors. So these are electrolytic capacitors. Let's see how close I can get. Yeah, these are little cans. They're just like through-hole capacitors, only they have a little plastic base on the bottom of them that turns them into surface mount. So what we see a lot of times now are all of these ones here. They're just flat, rectangular, these big guys here, these even bigger guys down here. These are all the normal ones. And the etched section on the end, that's the positive side. And it breaks from tradition. Tradition was always the negative side was marked, not the positive side. So we look at these here. We have markings on one side. Let's find out which side is which there. Actually, I could probably find out. Yeah, I bet all of these, we don't even need to open up a schematic. I bet all of these are connected from one side is going to be on ground and the other side is going to be on a power rail. And they're not going to be on the same power rail. So let's see. I'm just going to connect to ground, this screw right here. And let's see what side is this. That is the power rail side, because I have 21,000 ohms, 22,000 ohms. Let's go to this side. Short. So that is ground. The marked side of the electrolytics is the ground side. So I could probably go all the way over here. That one's ground. Go to this blue one over here. That one's ground. So yeah, the electrolytics, the marked side is ground. But then you even go to this one right here, and it even shows you that it has a plus on the marked side. The marked side is the positive side. And then the other side is your ground on those. Focus, you fuck. There you go. That must be a high power rail for 83 ohms. It's probably for the CPU. So yes, electrolytics are still marked. The marked side is the negative side. And then any tantalums, it's the exact opposite. The marked side is the positive side. Just to confuse the shit out of you when you're working on this. These two. See, this is when they first did it. Around here is when these things were really becoming popular, and you see that they marked plus on all of them, so that you're sure that, no, this is the positive. I know we used to do it this way for all these years, but now we are going to do it this way. And they let you know on these. But then fast forward a couple years, 10 years? This is almost. This is 7 years. No real markings. There's no plus on any of this stuff. There's just either the dot, the traditional dot for pin 1, or the grayed out marking for all of those. Interesting. Okay, this is cool now. We could test this. Take our charger, our amp meter, plug it in. What do we get? We're taking amperage again. Oh, look at that, 20 volts and 800 milliamps. So this board is now turning on. CPU should be getting a little warm. Yep. This board is good now. So that's all it was. That one little capacitor in this little group here died, shorted out, which then harmed the diode. So we changed those two things. This machine's now up and running. So that was a good just troubleshooting one. MLCCs, yeah. Crappy MLCCs. Multi-layer ceramic caps. That's what these little surface mount beige guys are. So they're just stacked on top of each other, little layers of the ceramic material that create the capacitor. And they're so thin, and they're trying to pack so much capacitance into such a little space that any irregularity in one of those layers, and it'll just short right through to the next layer. And little pop on it, breaks open. Either that or it's the end pieces where all the layers tie together. That a lot of times I think it might be that because it's always up against the edge that you see that little crack where it flakes off from. But yeah, the visual inspection. We didn't have to do so much troubleshooting once we knew where to look. Because you look at it, you see that little crack on the side of it. Yeah, I hope you enjoyed that. I hope you learned something. You know, keep troubleshooting, keep going. It's just the same thing every time. Every time you start troubleshooting one of these things, it's the same mentality, the same tool set every time. You need those three things. Always remember those three things. You need a safe place for the power to go. You need the enable for the chip to create the power, and you need the power to create it from. You need the supply to create it from. So always check those three things, and you'll find where your problem is from there. So, have a good day. Hope you learned something. Thanks for joining me.